In this video, we are going to talk about heaps, the different properties, how we implement heaps, as well as how we insert elements into a heap data structure. So let's get started. So binary heap is a complete tree that follows the property that each node is less than its children for a min heap, and each node is greater than its children for a max heap. So basically, a binary heap is kind of like a binary tree. That's the first thing. Another thing is it's a complete binary tree. And what I mean by complete is we have already discussed different types of trees. So a complete tree is filled up to the last level. And at the last level, like let's say if this is the last level, all the leaves are towards its left, which is they start from left to right. So this is a complete tree, while this is not, because you do not have a value right here. So to make it complete, you need to have all the leaves in the last level aligned towards the left side. So this is the first property of a heap, which is it's a complete binary tree. The second one is each node is less than its children, which is if we have a node X, this should be less than both its children. And this property is recursive, which is each node should be less than both its children. So since this property is recursive, we can confidently say that the element that is at the topmost is going to be either minimum or maximum, depending on which type of heap we are discussing. So throughout this lecture, we'll just discuss min heaps. For max heap, it's exactly the same, but just like whenever we are implementing any algorithm, instead of the less than symbols, you'll just use like greater than symbols. But otherwise, it looks exactly the same. So let's go back to the properties. So the first one was it's a complete binary tree. The second one is each node is less than its children for a min heap. So that means the root element is the smallest element. Also, the operations that are supported by a binary heap is extract min, which is you extract the minimum element, and insert operation, which we discussed in the previous video. So one thing to note is like there are different types of heaps that include like Fibonacci heaps, binary heaps, K heaps, or like D heaps. There are several types of heaps. We are just going to discuss the binary version, which is like pretty straightforward. So each node has like two children, and both of its children are greater than its parent, which is 8 is less than 18 and 29. 18 is less than 20 and 28. 29 is less than 39 and 66. And then 20 is less than 37 and 26. And 28 is less than 76 and 32. Similarly, like if you talk about any subtree, the root is going to be the minimum element of that subtree, and all elements which are below root are going to be smaller than that. So like the property is entirely recursive. That is one important thing to note. Now, how can we represent this heap? Like, let's say if we are creating this data structure in C++, we can create this heap node class, which has int value. It stores the value of the heap. This is exactly the value which we were discussing the priorities. Next, we have the left and right pointers or left and right heap nodes that store the left and right children. So both left and right here are min heaps in their own right, because we said that the property is recursive. So all of the left and right children are themselves going to be min heaps. Now, it seems that we can use this way to implement this data structure, but it gets much more messy. So another way is to use this property of complete binary tree. And in one of the tree representation lectures, we discussed that there's another way to represent trees in the form of an array, where you have this parent that is stored, and you have child 1 and child 2 that is stored right here. So if this is parent, child 1 and child 2 are stored next to it, and then you get some sort of equations. So instead of storing the binary heap in the form of classes and nodes, we can represent this neatly in the form of of an array. And this is possible because there's no spacing issues, because we know like all elements are adjacent to each other. So how we can represent this is you have this array that stores these numbers, which is like if this is the heap, the array will store all the numbers level by level, which is you have 8, then 18 and 29, the second level, then 20, 28, 39, 66, 37, 26, and so on. Now, this particular representation also has some formulas on calculating what are the children, what is the relationship between children and parents. So earlier we could get the relationships between children and parent using left and right, like nodes left would be a left child and nodes right would be a right child. So how can we like determine the relationships between child and right? These are the two equations. So for a node at position P in the array, like let's say if we talk about this 8, position is 0 for this node. This will have two children, like since every node has two children, that those are given by the formula 2p plus 1 and 2p plus 2. So since p is 0, it's going to be 1 and 2. And you can see at 1 and 2, we have these two children, which is 18 and 29. So if we go back to this heap, you can see 8 has two children, 18 and 29. Let's do one more. Let's say if we talk about this number 29, we know this node's children are 39 and 66. Also, this node that is 29 is stored at the position. Let's try to find this in the array. It's stored at the position 2. So we can find the left and right childs by 2p plus 1, which is 2 into 2 plus 1, which is 5, and 2 into 2 plus 2, which is 6. So here you can see that at position 5 and 6, we have 39 and 66. So that's how we determine the relationship between children. Also, you can find the parent, which is like if you have a position, like let's call 7, at position 7, we have this number 37. So if you want to find out the parent of 37, you can just use this formula, which is floor of c minus 1 divided by 2. So in this case, c is 7, so it will be 7 minus 1 divided by 2, which is 3. And floor of 3 is 3 itself. So the parent, let me just erase this, of 37 is at position 3, which is this one. So let's go back in the tree and see, which is 37's is right here, and its parent is 20. So you can see that the properties are being satisfied. And this way, like we can represent a heap in the form of an array. So let's talk about insertion, like how do we insert values into a binary heap? So the algorithm for insertion is pretty straightforward. Basically, you find out which is the last element in the array. So if you are storing these numbers in the array, level by level, there must be some space that's remaining in the array, right? Or there's some space for like these two places. And if this was also filled, there's space right here. So what you do is you add the number here. Like let's say if I was trying to insert 9, I just add 9 here or attach it to the last element in the array. Next, I now know I have violated the heap property because 9 is smaller than 66, so it should be its parent. So we need to do some magic to fix this. And that's where two different types of operations come into handy, which is one is called heapify up, and the other one is called heapify down. So we are going to use the heapify up in this set, which is when we are inserting an element, which is we are going to fix this property that the parent must be smaller than its children. And then we are going to use heapify down in our deletion. So here's the pseudocode, which is you insert the new element at the next position at the bottom of the heap. Next, you keep swapping the two elements till you fix the heap property, which is 9 will be swapped with 66 in this case. So 66 will go down, 9 will go up. Now 9 is still smaller than 29, so 29 will come down and 9 will go up. Now 9 will be compared to 8. 9 is greater than 8, so we have fixed this tree, or we have fixed the insertion. That's how generally like insertions work, which is you have, while new item is not at the root, which is the new item has not reached the root, you keep on checking whether it's smaller than its parent or not. If it is not smaller than the parent, which is it is if it is smaller than the parent, then you make a swap. Otherwise, you just stop right there, because then you have fixed this entire property.